strategy IV protecting groups. Protecting groups have been mentioned occasionally in previous chapters. In this chapter, the ideas behind their use are systematically presented in a collection of protecting groups suitable for a range of functional groups as tabulated. Protection allows us to overcome simple problems of chemoselectivity. It is easy to reduce the keto-ester 1 to the alcohol 2 with a nucleophilic reagent such as NaBH. That attacks only the more electrophilic ketone. Another important function of protecting groups is to prevent a reagent from attacking itself. In the last chapter, when we discussed the synthesis of the bicyclic amine monoamorine, we used the protected enone 12 but did not say how it was made. The chloroketone 9 is first made in 89 to 93% yield from the ketolactone 6 simply by reaction with HCl. Chloride displaces the protonated ester group 7 and the product 8 decarboxylates under the conditions of the reaction. Any attempt to make a Grignard reagent from 9 is DTOMED because the nucleophilic Grignard would immediately attack the ketone. We need to protect the ketone with an easily added group that is not attacked by Grignard reagents, and the acetal 10 is the answer. Addition of the Grignard from 10 to acrolein, CH2 equals CHCHO, gives the allylic alcohol 11, which is oxidized to the enone 12 with manganese dioxide. If you look back to chapter 8, you will see that the acetal was retained until it was very easily removed almost at the end of the synthesis. Any attempt to make a Grignard reagent from 9 is DTOMED because the nucleophilic Grignard would immediately attack the ketone. We need to protect the ketone with an easily added group that is not attacked by Grignard reagents, and the acetal 10 is the answer. Addition of the Grignard from 10 to acrolein, CH2 equals CHCHO, gives the allylic alcohol 11, which is oxidized to the enone 12 with manganese dioxide. If you look back to chapter 8, you will see that the acetal was retained until it was very easily removed almost at the end of the synthesis. Qualities needed in a protecting group: it must be easy to put in. It must be resistant to reagents that would attack the unprotected functional group. It must be easily removed. The last point may not be so obvious, but it is the most difficult to achieve. Many syntheses fall down right at the end because a protecting group cannot be removed without destroying the molecule. The next section looks at ways to make removal of protecting groups easier. Ethers and amides as protecting groups. Protection of alcohols and amines might look simple. Methyl ethers and simple amides are easy to make and are very resistant to a wide variety of reagents. So there is no problem in carrying out the required reaction elsewhere in the molecule, i.e. turning RIN13 and 17 into RN16 and 20. But sadly, they are almost useless as protecting groups because such violent conditions are needed to remove them. Cleavage of methyl ethers requires good nucleophiles. Under acidic conditions, and the hydrolysis of amides needs refluxing 10% NaOH or concentrated HCl in a sealed tube at 100 C overnight. This is also the key to the weakening of amides as protecting groups for amines. The amine is acylated with benzyl chloroformate 33, as described in chapter 5, to give urethane 34. This is still an amide on the left, but a benzyl ester on the right. Then the reaction is carried out. Hydrogenation cleaves the weak benzyl O bond to give unstable carbomic acids 36 that decarboxylate 37 spontaneously to give the altered amine R2NHC, though the C and bond is cleaved. No nucleophilic attack on the carbonyl group is needed. This protecting group is so popular it has its own abbreviation, CBC, carbobenzylox C, or even just C. Both benzyl and CBZ groups are used in the synthesis of aspartame 38, the dipeptide that is 150 times sweeter than sugar and used in many soft drinks under the name NutraSweet. Only one disconnection is reasonable, the amide bond in the middle of the molecule suggesting derivatives of available aspartic acid 39 and phenylalanine 40 as starting materials. Since we need the methyl ester of phenylalanine, no further protection of that starting material is needed, but the amino and 1-carboxylic acid group of aspartic acid need to be protected and the remaining acid activated. The CBZ group is perfect for the amino group and both acids in 41 can be esterified with benzyl alcohol. Ester must be cleft and not the other. This looks difficult and cannot easily be done by hydrogenolysis, but peptide chemists knew that the right one was hydrolyzed in base to give the required intermediate 43. Evidently the amide makes that ester more electrophilic, but this was discovered by experience. Now the free acid must be activated towards nucleophilic attack. The trichlorophenol ester 44 is ideal. 0.6. Coupling requires only a weak base of the benzyl esters are removed by hydrogenation. The benzyl esters are there for protection, but the trichlorophenol ester is there for activation, making that ester more electrophilic than the benzyl ester in 44 or the methyl ester in 40. Relative to CBZ is butyloxycarbonyl. It uses a different method to make esters easy to hydrolyze. It is added to an amine or an alcohol by the chloroformate 46 and, after the reaction, hydrolyzed with acid, no water being needed. The ester is protonated and the R-butyl cation drops out in an SN reaction 49 to give the same intermediate 36 as in the removal of the CBZ group. Of alcohols, we have already mentioned the THP group, but by far the most popular protecting groups for alcohols are the various silyl groups. You will already be familiar with the MEC or TMS trimethylsilyl group, but this is little used for protections as it falls off so easily, often just during chromatography. More hindered is the triethylsilyl TES or tri-isopropylsilyl tips groups and ibutyl dimethylsilyl TBDMS or misleadingly TBS, and, most hindered of them all, R-butyl diphenylsilyl R-bufac. They are usually put on with a silyl chloride and a weak base, often imidazole and DMF, and they can be removed with oxygen nucleophiles, often in acid solution.